अच्छा चलें जस्ट थोड़ा सा पिछला वाला रिकैप कर लेते हैं कि अच्छा रेट में ज्यादा चीजें नहीं है। क्या क्या किया था? वी डिड हेटेरोजेनस होमोजेनस कैटलिस्ट लास्ट क्लास, ठीक है। व्हाट वाज रेट? रेट वाज कि एनी चेंज विद रिस्पेक्ट टू टाइम, ठीक है। कलर, मास, वॉल्यूम ऑफ गैस, कंसंट्रेशन, कुछ भी। Most popular one is basically you'll always see rate is change in concentration with respect to time. As anyways, I told you the change. One way to measure the rate of reaction is you can plot change with respect to time. Okay, and it could be an increasing change, it could be a decreasing change. For example, the mass of Mg is decreasing, and the volume of H2 gas in this particular reaction is increasing. So the gradient of this graph is the rate of reaction. So the gradient of the curve is equal to the rate. The gradient could be negative, it could be positive, it could be increasing, it could be decreasing. So we ignore the negative and positive signs, okay? We just focus on the steepness of the gradient, okay, not the direction of the slope. So that was one way of measuring rate, and then you had another way of measuring rate, and that was you don't plot a graph. Instead, what you do is you fix the change, okay, and you figure out what is the time that is required for that change to happen. For example, time taken for 5 cm cube of H2 gas to form, so that's rate would be 1 over time. If the time is less, then the reaction is fast. If the time is more, then the reaction is slow. Okay. So this is one way of measuring initial rate directly, and we are always comparing initial rates of reactions. Okay. And we did autocatalytic reactions, etc. Okay. So now we figured out two ways of. Yeah, the clear था ना सारों? Ikshita, is this clear? Minahil, Zaina, is this all clear?
Yes, sir.
Acha, so now we're going to talk about orders of a reaction. So order of a reaction, or specifically order of a reactant. ठीक है, there's an overall reaction order, and then there is order with respect to each reactant. Acha, so what is order of reaction? So let's say you've got a reaction, and there is X and there is Y, and these are reacting, and they're producing something that's Z. So typically what happens is that the rate of the reaction depends on the concentration of the reactants. So rate of the reaction depends on concentration of the reactants. Do you remember square brackets? That is concentration. Normally what happens is a higher concentration, we've learned that if there's a higher concentration of reactants, you're going to have more frequent collisions. Afan, kya hua? Yes.
Sir, could you scroll up for a second, please?
ठीक है. I mean, just this. We just started order of reaction. This was from the
Okay.
previous class.
Okay.
अच्छा, नहीं, Afan, do you have a question?
नो सर।
अच्छा,
अच्छा वो गलती से हो गया।
ठीक है. अच्छा, so higher concentration, more frequent collisions, and you should have a faster reaction. Or, I mean, that's the common logic, right? You got higher concentration, you're going to have more particles, you're going to have more frequent collisions, and technically you should have a faster reaction, but not always. Okay, so sometimes having a higher concentration does not affect the rate of reaction. So this relationship that rate is I mean, this particular relationship, the one that I'm highlighting over here, this is not a straightforward relationship. It's not that you have a higher concentration of reactants, and I'm going to explain why. It's not always that you have a higher concentration of reactants, you're going to have a higher rate. So the proper way to describe this relationship is that rate is proportional to the concentration of the reactants. The reactants in this case are X and Y. But they're going to have some power. There's going to be, and that power is A and B. So it's not that it's a straightforward relationship that rate is proportional to the concentration of the reactant. It's going to have, and even over here, it's going to have some, and that's known as order of reaction. So it's going to have some power over here. So the exponent that describes this relationship, that's the order of reaction. So it's referred to as the order. TK, and we're going to take a deep dive just now, TK. I haven't explained anything right now. And if I get rid of the proportionality, there's going to be a constant. So the rate of the reaction is dependent on the reactant, the first one, A, and it's dependent on the reactant, Y, which is B. Now this over here is referred to my rate equation. This is what you call a rate equation. Here's the first thing, very basic. Rate equation is pretty simple. That you've got two reactants, the rate of the reaction is dependent on the concentration of those two reactants. So rate is dependent on the concentration of X. It's also dependent on the concentration of Y. You get rid of the proportionality, you're going to bring in K. That's a constant. Or that specifically is the rate constant. That's referred to as the second score. So that's referred to as the rate. So this is your rate equation and K is your rate constant. Anyways, my focus is on A and B. Like what do the powers A and B tell you? That's what my focus is. Let me technically write the definition of order of reaction. So order is, I mean, the technical definition is, I mean, it's simple. It's the exponent. They're going to ask you this. So it's the exponent of the concentration of a particular reactant in a rate equation. Okay, so that is what the technical definition of order is. Achha, is this, I mean, just the basic idea. Is this rate equation clear to you? That rate depends on the concentration of X and concentration of Y, right? The constant is just to get rid of the proportionality. And I'm going to explain what this order, what do A and B represent. But is this clear? The first part, is this clear?
Yes.
Yes, sir.
Okay, now the next part is what do we mean by this A and B, right? The powers, right? The orders. So the first one is order. Let's start with order one. If some reactant is order one, what does that mean? For example, if I just explore this fact, that rate is dependent on the concentration of X and the power is one. So what is that relationship? That's just directly proportional, right? So it means that you increase the concentration of the reactant, the rate of the reaction will increase. So that's the simplest relationship, directly proportional. Because that means the rate of the reaction is directly proportional to the concentration of the reactant. So you increase the concentration of reactant, then your rate of reaction or your number of collisions would increase proportionally. So it increases proportionally. So that's the first thing. So whenever I say order one, that means rate is dependent on the reactant concentration, and the power is one. That means it's directly proportional. If I double the concentration of X, the reaction would be twice as fast. If I triple the concentration of X, the rate of reaction will be 3 times. If I increase the concentration 10 times, it's going to be 10 times. The rate will increase 10 times. So that is what is meant by order one. Is that clear?
Yes, yes, sir.
Okay, so that's order one. The graph for rate versus the concentration of X would look like this. It's going to be a linear graph. Okay, directly proportional, so it's going to look like this. The rate will continue to increase if you keep on increasing the concentration of X. Uh, there's another graph as well, which is known as the half-life. And that graph is that if I plot now listen to this now try and understand this graph very carefully. So if in the reaction, remember X is my reactant, and this is time. Normally what happens is in a reaction, like this is the original equation, right? So if X gets used up, the reaction should slow down. I mean, order one means that. Order one means that the reaction is going to be very fast in the beginning because you've got a lot of X in the reactant side. And then slowly the X will get used up, the concentration will decrease, and the rate of the reaction will also decrease proportionally. So, so what happens over here is that initially the reaction would be very fast. So so my concentration of X is going to be maximum at the beginning. TX if so let's say it's starting at this point. The reaction would be very fast in the beginning because the concentration of X is very high. So where's the halfway mark? Just a second. Now this is known as the half-life. It is the time that is required for the concentration to decrease by half. So what happens is that the reaction is very fast in the beginning, so the slope is going to be very steep. X gets used up very, very quickly. But when X gets used up, the reaction slows down, right? Because it's order one. X gets used up, the reaction slows down. So then you're going to have the next half-life, which should be just a rough guess. It should be somewhere over here. So the reaction, and I'm going to explain the half-lives very soon. So the reaction slows down. Now X gets used up, the curve is going to become less and less steep. The reaction then slows down further. Okay, so then X gets used up even more and the reaction starts slowing down. The concentration decreases, the curve becomes less and less steep. So it's eventually going to look like an asymptote. This is what the curve would look like. So what is happening is that your curve is becoming less and less steep as X gets used up. This is known as the first half-life. This point over here. This over here is my second half-life. This over here is the next half-life. And then I have my fourth half-life. Achha, what's a half-life? Half-life is the time that's required for the concentration to decrease by half. And that's exactly what's happening over here. You started over here. It took this much time for the concentration to decrease by half from this point to this point over here. So that was the concentration of X decreasing by half. The next time the concentration decreases by half, that's this tiny bit over here. And then you reach this point. Then the concentration decreases by another half. So that's this third half-life. Then the concentration decreases by another half. So every time the concentration is decreasing, the reaction is slowing down proportionally. Remember, this is first order. Rate was actually dependent on the concentration of X, and it was directly proportional. So right at the beginning, the reaction was very fast. It was very steep. You had a high concentration. The rate of reaction was very fast. So it decreased very quickly. And then it started to flatten out. It started slowing down. As X got used up, the rate of reaction became slower and slower. Now, the typical graph of a concentration time graph for a first order reaction is going to look like this. It's going to have constant half-life. That every time for the concentration to decrease by another half, it takes exactly the same amount of time. Is this clear?
Yes, sir.
Yes, sir.
ठीक है, because the reaction keeps on slowing down. So that's your typical first order reaction. And to identify a order reaction, you can just measure the half-life, how much time it requires for the concentration to decrease by half. If every time it's always the same, that means it's first order. That means the reactant concentration and the rate of reaction are directly proportional. ठीक है, first order, is this clear?
Yes,
Yes, sir.
sir.
ठीक है, सारों के
Yes, sir.
मिनाइल बाकी जो है, is this clear? So as the next one, we're going to focus on order zero now. What do we mean by order zero? If a reactant has zero order, so that means the rate of reaction, it depends on the concentration of X, but the power is zero. So what kind of relationship is that? That means that the rate of reaction doesn't really care about X. You put in whatever the concentration of X is, whether X is having a higher concentration or it's having a lower concentration, anything to the power zero is going to be one. So the rate remains completely unchanged. So rate, so this relationship means that the rate does not depend on the concentration of X. Nothing would happen to rate, whether X is high in concentration or X is low on concentration. The rate is not going to change. So if I make the two graphs again, one is the rate, and so one graph is the rate versus concentration graph. So if I keep on increasing the concentration of X, the rate of the reaction will completely remain unaffected. Its value is not going to change. ठीक है, so it doesn't change. Is this clear?
Yes, sir.
Yes, sir.
ठीक है, so the reaction is not going to be affected. And similarly, the graph, the how would the concentration of X vary with respect to time? So you've got X. Now remember, that's your reactant. It's getting used up. And here's your time. So the speed with which the X is going to get used up in the reaction, it's just going to be constant. The reaction will not slow down. Remember, the reactants are going to go to zero eventually. They were going, they were going, they were going to zero in the first one as well. But in that case, the rate was dependent on the concentration of X. So when X got used up, the reaction started slowing down. But over here, the reaction is not going to get slow. It's not going to slow down. So the speed remains completely constant. The rate does not change. So rate, it simply does not change. Remember, the gradient is the rate. As X, your reactant gets used up. Is this clear?
Yes, sir.
Okay, so that's your zero order relationship. Uh, your rate remains completely unchanged, unaffected. And then you have an order two relationship. So order two is your rate will be too much dependent on the concentration of X, your reactant. So it simply means that your rate is very sensitive to X. It means it's not directly proportional. It's actually like what this relationship means that if you double the concentration of X, your rate is too sensitive now to X. Your rate of reaction will become four times. So rate increases by four times. You triple the concentration of X, your rate of reaction, you increase the concentration of X, your rate of reaction will increase nine times. And the reverse is also true. If you decrease the concentration of X, so for example, if I if I decrease the concentration of X by half, the rate would become one fourth. So not only will it speed up a lot more, but it will also slow down a lot more as well. Is this clear?
Yes,
Sir.
sir.
Okay, so how would the graph look like? It's going to look something like this. The first one second. Okay, so the concentration time graph, right? So concentration rate graph. So that's going to be an exponential graph. It's going to go upwards. It's not going to be linear. You increase concentration of X, the rate keeps on increasing by a much bigger margin, right? And then your half-life graph. Remember, as X gets used up with respect to time, as the reaction proceeds and X starts getting used up, now the rate will slow down a lot more. So, for example, you're starting at this point. This is your starting point, and the first half-life is somewhere over here. This is your first half-life. This is the time that's required. So initially the reaction is very fast. Second half-life, but then the reaction starts slowing down by a much bigger margin. Then your third half-life, uh, that's going to be there four. So that's going to be four, and so it's going to be somewhere over here. So every time the half-life continues to increase because the reaction is slowing down too much. So every time it just takes a longer and longer time for the concentration to decrease by half. Next half-life, that's going to take a much, much longer time. And the next half-life, that's going to be much bigger as well. So every time what's happening now is, well, in the beginning, the reaction was like very fast. But then as X decreases, so if the concentration decreases by half, the rate of reaction uh, decreases by one fourth. Is this clear?
Yes, sir.
Yes, sir.
Okay, so let me. So it just decreases a lot more. And it takes a longer and longer time for the reaction to finish. So every time the half-life continues to double. So this was the first half-life, this was the second half-life, this was the third half-life, this is the fourth half-life. doubles. Concentration gets used up, just takes a longer and longer time for the reaction to finish. So remember, you've got these three orders and you've got these three graphs. So one way to figure out what the order is for a particular reactant, you can just look at how the concentration changes as it decreases, how the rate of reaction changes, and how does the curve look like when the reactant gets used up. Uh, if it's constant half-life, that's order one. If it's just a straight line and the rate of reaction completely remains unaffected, unchanged, as X keeps getting used up, that's order zero. And the last one is order two. That's when it just takes every time it takes a longer and longer time. So that means your rate is too sensitive. It means that it's got order two. Okay. So are these things clear? The orders of the reaction. Is this clear?
Yes, sir.
Okay, so that's method number one. Okay, method number one is, remember, there are three total methods of finding the order of reaction. So this was method one. In any question, there are going to be three methods. Okay, so method one is, I'm just going to write that down. Um, order zero. Order one is constant half-life. Order two is half-life doubles. Takes longer every time. Order zero is half-life it gets halved. Every time it's going to be half of the previous one. It's a straight line. I mean, you don't even have to check the half-life. The shape would be sufficient. But this is what it's going to look like. This is the first half-life. The second half-life would be a lot smaller, right? That's your first half-life. The second half-life is now a lot smaller. The third time the concentration decreases by half, that's even smaller. So every time the half-life is becoming less and less. Okay, but you don't even have to check the half-life. If it's a straight line, then that's obviously order zero. So, the next thing is we're going to look at method two, and we're going to try and understand why does rate not change if the concentration changes, or why is it sometimes too sensitive? Remember, we just studied that whenever you increase concentration, the rate of reaction should increase. But order zero is suggesting that it's not going to change sometimes. Sometimes it's going to change in a directly proportional manner, and sometimes you change the concentration, the rate of reaction will change a lot, right? So, how do you get three different orders? So it all depends on mechanism of a reaction. So mechanisms are the other method of finding the order of reaction. If you know the mechanism, you can look at the mechanism and you can tell what the order of reaction is. अच्छा, जोहेर आवाज आ रही है. अच्छा, Amna, Akshita, is this clear up till this point? Any questions?
Yes, sir.
Yeah, it's
Okay. The next thing is, we learned that concentration increases, the rate of reaction should increase, right? But research suggested that it might not increase. So why is that? So it all depends on the mechanism of the reaction. So I'm going to take an example of a mechanism which is the SN2 or SN1? Just one second. It's the SN1 mechanism. Not sure if you remember this. This one was for tertiary halogenoalkanes. I'm going to write it. I'm going to just tell you what the mechanism is. So in tertiary halogenoalkanes, what happened was that if you have, I mean, this was the overall reaction. I'm going to draw the overall reaction first. So if you have a tertiary halogenoalkane and there's a Cl and it would react with NaOH aqueous, so let's say there's OH minus one nucleophiles, the OH minus one nucleophiles will knock out the Cl and they would substitute the Cls. And you're going to get OH and the Cl is going to get knocked out, right? So that's your overall mechanism. And this overall mechanism had two reactants. You had your halogenoalkane and you had so your rate of reaction, if I write the rate equation, your rate should depend on the halogenoalkane, three methyl groups with a carbon and a Cl, and it should depend on its concentration, and it should depend on the concentration of OH ions, right? Because if I increase the concentration of OH ions, the collisions would increase, the reaction should become faster. If I increase the concentration of the halogenoalkane, the collisions would increase and the reaction should become faster, right? But in reality, what happens is that the rate of reaction is only dependent on the concentration of the halogenoalkane, and it's not, zero means it's not dependent on it, right? So it's first order with respect to the halogenoalkane, and it's zero order with respect to OH ions. So that means no matter how much I increase the concentration of OH ions, the rate of the reaction it simply does not increase. So why is that? So everything now depends on the mechanism of the reaction. So what's going on? Because the reaction is not as simple. It's no reaction is a one line. Like whenever you see an equation and you see a one line equation, reactions happen in steps. They're not one line equations. So this is not how the reaction goes on. The reality is the reaction has two steps. It's got a step number one, and that step number one is that a carbocation gets formed. So what happens is that you've got a halogenoalkane, a tertiary halogenoalkanes, and it's got a Cl, and the Cl gets knocked out. Maybe during collisions, it gets knocked out, and it ends up forming a very stable tertiary carbocation. Just one second. Achha, so it forms a very stable tertiary carbocation, and the Cl gets knocked out. And then you have a step two of the reaction. In step two, what happens now is that the carbocation then goes and it binds with the OH ions. So you had a tertiary carbocation. Ignore the fact that even if you don't know any of this mechanism, I mean, I'm writing down all the mechanism myself. Okay. So we're not getting tested on the mechanism itself. So the OH ion comes in and binds with the carbocation, forming the alcohol. So that's your whole process. It's a two-step reaction, this reaction. Now, since it's a two-step process, the two steps don't have the same speed. One of these reactions is faster compared to the other one, especially the second one. That's our fast step. Why? Because a negative ion will very quickly get attracted to a positive carbocation. So that's a fairly fast step. And let's give it some time. For example, it takes 1 second. Just hypothetically speaking, TK, let's say it takes 1 second for that step to happen. And the first step is a very slow step because it takes time for the Cl to break away. So that's our slow step. Now, when reactions happen in steps, it's like a relay race. Okay, it's one thing happens, then another thing happens. One step is going to be the slow step, the other one is going to be it's going to be the fast step. Now, your rate of reaction or your speed of reaction is only dependent on one of these steps. Which one do you think would it be dependent on? Would it be dependent on the fast step or would it be dependent on the slow step?
The
Slow
slow?
steps.
Okay, like if it's a relay race, right? There are four runners running, right? If there's a very slow runner, right? So the whole race depends on that slow runner now. Because right now, what is the overall time that's required for the reaction to happen? That's 101 seconds, right? So if I focus on the fast step and I try to speed that up, like let's say I speed it a million times and it's now taking 0.001 second, right? What effect would that have on the overall speed of the reaction? Now it's taking me 100 point, I mean, that's a negligible effect, right? So the point is the rate of the reaction will not depend on the OH ion concentration because if I increase the OH ion concentration by a million times, right, the slow step will not speed up. Nothing will happen to the slow step. The only reaction that will speed up is the fast step, right? Because the OH ion is not doing anything in the slow step, in the first step, right? The OH ion only appears in the second step. So if I increase the concentration by a million times, even if the fast step speeds up, right, and takes a lot less time, the overall reaction speed barely gets affected. Is this part clear?
Yes, sir.
सर ये जो Cl आयन जो होता है it gets knocked out because of collision, right? So
हाँ
if there is more concentration of OH तो ज़्यादा collision होगी तो ज़्यादा कार्बोकैटायन नहीं बनेंगे.
नहीं लेकिन OH is not doing anything over there ना collisions आपस में it's collisions between uh,
हाइड्रोजन में क्या.
with anything ना मतलब it's not
अच्छा
necessarily OH ions ना वो तो साथ वाले के साथ भी collide कर सकता है ना you get my point like it could
सही.
collide
अच्छा
with the walls of the container as well right so so the point is whether there is OH there or there's no OH there the first reaction is not affected by OH ions
अच्छा
ठीक है do
सही.
you get my point well water if it's probably aqueous solution right so there's probably water molecules as well so it could be due to any collision with the walls of the container with the water molecules so it could be because of any collisions right so anyways so the point is that a reaction happens in steps. Okay? A reaction is more like a relay race. There's going to be a slow runner and there's going to be a fast runner, right? So the rate of the reaction does not depend on the fast runner. It all depends on the slow step. Okay? No matter how much you increase the speed of the OH, and so this is the point, main point is that any reactant that's in the fast step, that's zero order. Any reactant in fast step is going to have zero order. It will not affect the rate of reaction. Or it will affect the rate of reaction, but the effect will be minimal. It's going to be very less. Any reactant in fast step is zero order. I said now, what if I increase the concentration of this halogenoalkane? Then what will happen? Uh, more collisions, the more chances of Cl getting produced. The reaction will speed up, right? You have a higher concentration of halogenoalkanes. The reaction would speed up, and let's say it speeds up and it speed doubles, right? 50 seconds now. So what is now happening to the overall speed of the reaction? So all of a sudden from 100 plus 1 second, it's now 50 plus 1 second. So all of a sudden it's gone. So that means the rate of the reaction is going to be affected by the concentration of the halogenoalkane. So any reactant that's involved in the slow step, it's going to have order one. The rate of the reaction will be dependent on that particular reactant. Is that clear? ये clear है?
Yes sir.
So any reactant in slow step has order equals 1. Okay, that's the first thing. So slow step, fast step reactants, any reactant involved in the fast step, it's going to have 0 order. Any reactant that's involved in the slow step, that's going to have order 1. So remember, reactions happen in steps. Okay, I'm going to come to order 2, but we don't have time for order 2 at the moment. But is this part clear? That what
Yes, sir.
determines the order of reaction? Is this part clear to everyone?
Yes, sir.
ठीक है, आमना clear, Minahil, Zuhair?
Yes.
Yes, sir.
ठीक है.
Sure.
So then let's continue with this with order 2 then. Okay, how does the mechanism determine whether something is order 2? How does order 2 come about? Okay, so we'll talk about that tomorrow then. Okay then. Take care, everyone.
Bye.
Thank you, sir.